Perfect. All right, so we should be all good to go here. So welcome everyone to the first workshop of the McGill AI Learnathon. So this workshop is going to be about math in machine learning. And our presenter is Sandi Mak. So Sandi Mak is a teacher and former department coordinator in the mathematics department at Montreal's Vanier College. She previously organized and taught a machine learning seminar accessible to CEGEP students and is currently involved in a project at PIA, which stands for, okay, now let me try to pronounce this, Pôle Montréalais d'enseignement supérieur en intelligence artificielle, which aims to use AI to match the skills sought by AI industry employers with post-secondary courses and programs. So without further ado, I will give the floor to Sandi to kick off this talk.
Hello, everyone. Thank you for coming. I realize that there's some really strong competition in my time slot. Dr. Rolnick is giving a wonderful talk on AI climate change, and I'm also the talk right before lunch. So I'll try to make this as interesting as possible. My talk is originally, when we planned it about 3 weeks ago, it was supposed to be about mathematics in machine learning and how they could be applied in AI. To be quite frank, that's basically 17th century mathematics. And I figured in an AI conference, that might not be interesting. So I promise that there is some math, but we're going to be actually looking at the latest and greatest thing in the NLP world, which is encoders and decoders. And these are really cool transformers, which basically process text. We're going to actually look at why these things are sort of the kings of these sequence modeling and why they're beating out the former architectures like RNNs, gated networks, and LSTMs. I promise there is some math, but it's not going to be super heavy on the math. I'm going to turn off my camera so that way we can focus more on the slides than me trying to talk, and you see mini motions here and there. So, okay, hang on, I just got to stop video. Okay, great. All right, so essentially here's the overview of our talk, and it's going to give you sort of an idea of what like a high level NLP system is going to be. We're going to look at examples of encoders and transformers. We're actually going to also look at something called the attention mechanism and then try to wrap up where things are. Because I don't know what level of understanding you have on NLPs or encoders or transformers or attention mechanisms, I'll try my best to give as much detail as possible. So the paper that this talk is actually based on is this one, Attention is All You Need. And essentially, it was sort of a seminal paper back, which came out about 3 years ago, that showed the power of having self-attention in a encoder decoder transformer. So if you've never played with a text generator, basically what these encoders and transformers can do is not only can they create chatbots, they can make better search engines. They can also generate text and basically do some really cool things. And so if you've never seen a text generation transformer before, basically what you do is you need to feed it some input, and it's going to use the previous input to generate a sentence. So here we're using a text transformer where you're going to feed it a sentence called, it was a dark and stormy night and the moon was. So that's the classical way we start horror stories. And then the transformer will use the seeded sentence to push out a suggested text. And the difference, again, I mean, you know, the sentence isn't bad, like shining brightly. It seemed to me that there was bright gleam of light in the distance and so forth. I mean, yeah, okay, it's not great. I don't think it's going to be a New York Times bestseller anytime soon, but I mean, the idea is quite interesting. If you want to play with some of these things, there's a lot of websites which allow you to kind of get a hands-on feel. I went to Hugging Face and they're using GPT-2 as the the foundation for making this transformer. So this thing where when we're generating these texts, what's actually really interesting is that the model is generating the sentence word by word, and it basically has the ability to attend to certain words as the text is being generated. So if we look at how it attends to the different words in the sentence, it's basically trained through backpropagation. And the upshot is that it really doesn't suffer from the the problems that LSTMs or GNs or RNNs have, right? So if you sort of look at the old way of how things were being developed with, say, RNNs, if the sequence is long, you just wouldn't be able to kind of access these sentences, these words which were generated earlier. Other models seem to do a little better, but they sort of have this memory deficiency, right? So you don't have that kind of history in order to generate that sequence or longer windows of context to draw from. So in theory, if you have like infinite computing power, and you have this attention to attend to things, you can actually, in theory, generate huge, use, say, a longer text context window to generate future words. So the transformer neural network that we're going to discuss is from that paper, Attention is All You Need. And in that paper, it basically demonstrates the power of attention and self-attention in these architectures. So what we're going to do is we're actually going to go through how this stuff is, how the input text or the source text is pushed in. It's going to go through the encoder, which is on the left-hand side. And then we're going to discuss how the decoder, which is located on the right-hand side, how that is going to sort of take in the inputs and then produce these output text. Right. Okay. So in order to kind of make this a little more easy to understand, we're going to create a dialogue completer. And I don't know about you folks, but I've been binging a lot on Netflix. Just we ain't going anywhere. So besides working and sleeping, just lots of Netflix and TV. So what we're going to do is we're going to feed our model the first part of a dialogue and sentence of quotes from, say, famous movies. And then we're going to train it to complete the back end of that sentence. Okay, so just to, again, I mean, we can pick different sentences to train our model on. I'm just going to use the one from John Wick, because I like Keanu Reeves and I like Lawrence Fishburne. And so the sentence that we're going to feed in is, you want a war or you want to? And then the machine is going to produce some type of output text. At the end, we're going to look at what happens when we actually do feed this in and see the results. It's actually quite interesting. All right. My apologies. Okay. So the question is, all right, so what are we going to feed into this? We have a source text. And so the idea here is that machines don't understand English. So we'll need to find a way to convert that into numbers or matrices. So our input statement is you want a war or you want to. And basically what we need is we have a vocabulary list. And you can imagine this to be, say, the list of all the words in, say, Wikipedia, which is like millions and millions and millions of words. Each one is going to be attached to an index. And so for every single word you have in your lookup table, you have an index that is matched to that word. And essentially that's basically what we're putting in to our vectors. All right, so again, you only want the ones that actually show up in the sentence. And so here's me writing them in a vector form and then me putting them out with the indexes. All right, so and basically that's pretty much it. This is what gets fed into the start of the encoder part. Next, we're going to move on to the input embeddings, right? So now that we've fed these indexes in, what are we going to do with it, right? And so that's in the input embeddings. And it just, at the beginning, every single word has a vector that is associated with it. And the numbers are actually randomized at the beginning. So through training, you usually do get some better representation. So these are just arbitrary at the beginning. So what I'm going to do is I'm just going to pick a single word from our sentence. Let's say we use the word war, and we're going to say that there's like 5 dimensions. And you're going to ask, well, what do these dimensions mean? And they actually try to capture some type of linguistic feature for that word. So for example, is it like a noun? Is it named entity? Is it a verb? Something like that. And so then what it will do is it will try to sort of look at these features and decide how to kind of work those numbers out. So if you have, like, say, 2 words which are similar, like war and gun in this context, what ends up happening is that at the beginning they kind of look like these numbers are arbitrary. They're just random. But after time, when you train, presumably these words, because of their similarity, they get closer and closer. And that takes a couple rounds of training. So in our input embeddings, here again, you just really want to focus in on the words which are in your sentence, right? And so we have these input embeddings, and then sorry, the indices get put into the get fed into the input embeddings, and then we need to basically add some positional information. So that's here. So positional embedding. So we need to find, so after we've sort of got these indices on where the word shows up in our vocabulary list, and then looked at the different features of the words, i.e. are they like nouns, are they verbs or something like that? We now need to basically put through positional information. So as before, we could look at LSTMs, but the problem here is that they take these vectors in sequentially, and that's going to take like a super long time, right? So, it's computational cost, that's going to be insane, and it's going to take us forever to even just process one of these things. So they're quite slow. That's the downside. What about transformers? What did they do? Well, they take all of the vectors in one go. So that's a heck of a lot faster than trying to do this sequentially. But then what's the downside? Well, the downside is that you lose that positional information for where those words were in the sentence. The LSTMs preserve that. Why? Because you're actually getting that in sequence. They're going like one at a time, so you know that this word is like second in the sentence, this word is third, and so forth. But when you do transformers, because you're taking them all simultaneously, you lose that critical information. So then you're going to say, well, why does like position matter? Here are 2 sentences. Even though she did not ace the final in calculus, which is, by the way, 17th century mathematics, she was not happy with her performance. And then we look at the other sentence. Even though she did ace the final in calculus, she was not happy with her performance. So just this one word in a different place could change the sentence entirely. And so you do, like, order matters in this case, right? So I think, like, in some courses you've taken for mathematics, order matters, right? So now the $1,000,000 question: well, what the heck do we put in these positional vectors? What kind of information should we add to the embeddings so that we have a vector that not only gives us the embedded information, not with, like, say, the features of the word or and the position. So how do we basically squeeze those things together? Here's the first naive approach. We just straight up add the positions for the sentence where the word shows up in the sentence, right? So, like, a position 0, where you're just going to fill the entire vector with zeros. By the way, just for a demonstration, the dimension I'm using is 5 because it fits on my screen. the fine folks from Google who wrote that wonderful paper used, I think, 512. So clearly that's not gonna fit this the screen. So what you can do is you can just add all of that positional information with just quantities like this. But here's the problem. I mean, when you add numbers like the longer the sentence is, the larger these numbers are going to be, and you really don't want to distort your information that way, right? So adding huge numbers at the end, that's not going to be good. Okay, so what happens if we don't want to add like super large numbers? Can we scale it? So the question here is, if we're going to scale, how are we going to scale? One consideration could be we look at the length of the sentence, and then we subtract 1 and use that as sort of a percentage. And then we just multiply the positions and then add it to the embedded vectors. Okay, so we solved the problem that we're not going to get these super large numbers, but then we have another problem, right? So it's sort of like whack-a-mole when it comes to doing these problem solvings, right? You got this great idea and then these problems crop up. So what's the problem with this idea? The problem is that if you actually have two sentences which are of different length, and that's highly probable, the positional information gets, the position vectors get, the numbers change, right? So this is a sentence of 11 words and this is a sentence of 21 words. What you really want is that even though there's only a 10-word difference, notice how the position values in each of these vectors have changed dramatically. And you actually really don't want that, because that's going to cause problems in your model in the long run. So the folks who wrote that paper on attention is all you need had this really clever idea of combining two functions to basically give us this information of position without having any of the difficulties encountered by, say, adding like huge numbers or distorting length. Essentially, you want this position to be static. Okay, so so this is where the math is, and this is basically everybody's favorite part of mathematics, trig. So again, in dimension 5, what we're going to do is we're going to have these indices. So let's say we have the position, and we have these indexes, which basically represent the position on this. Excuse me. So if we look at a sine curve and we draw, fill in the positions and compute the index against the dimension, what you could see is that if you were to plot the different position vectors into the sine curve, yeah, you're getting some differences, but the downside is that something like position 3 and position 6, clearly those are two different spots on your sentence, they kind of get mapped to the same height. And we're using the height as a proxy to basically tell us where that word is in our sentence. And that's not really good, because clearly position 3 is different from position 6. And the same thing could be said about a word that shows up as the 6th word or 7th word in your sentence, and then something that's further down on, say, the 14th. You want these mappings to be different. So how do we solve that? Well, we're just going to use lots of different sine curves or cos curves, but with different wavelengths, right? Or different frequencies. If you use different wavelengths, then you sort of have this ability to sort of distinguish points from each other. So if we kind of look at the unadulterated version of the sine curve, when two values are close together along the word position axis, they're still kind of close together. As you kind of move further out with higher frequencies, you can start to see how the heights differ. And of course, like further down, if you go even further, so something that's 30 words long, you can see the differences show up a lot faster, right? So on the green curve, we can see that the difference between the word position, we're basically able to extract the positional information using higher frequency curves. So this is a little more apparent if you look at what happens if you're comparing, say, two positions with different indexes. So at index 4, we're kind of still close. And then as soon as we get to index 0, we finally have a good differentiability on for distinguishing positions. There's a bit of a spoiler alert with the with this paper. Not only do the authors use a sequence, just the sine curve, they also use the cos curve. And the way they decided how to set that up is that whenever it is even, they use the sine curve to compute the position embedding, and whenever it is odd, they use the cos. They also use the sine and cos functions because there are sort of linear properties that the model can learn if they use these terms. Okay, so back to our statement. John says, you want a war or you want to? And then we have the correct, we have the embeddings, we have the position information, and then we can add them together, and that will give us the embedded position. Moving on, so basically, this is what happens, right? If you want to imagine what happens when we actually take those vectors and put them into the embedding. Okay, so now we're going to get into the really cool part of the encoder, the multi-headed attention. Pardon me. Okay, so why you're going to say, well, what the heck do we even need attention? So here's a statement. Why, it's elementary, my dear Watson. And now if I asked you, who said that? If you know anything about 19th century literature, you'll know that it's Sherlock Holmes who said it. And the interesting thing is that your mind is probably not paying attention to all of the words. If you just know the word, if you just look at the word Watson and elementary, then you automatically know who said that quote. So you don't actually need all of that information. Some words you attend to more than others, and you're paying attention to them more. So think of that like a filter. Here's another one. Okay, so that was attention, old school. Now let's look at self-attention on steroids. Okay, so we're going to look at a sentence called, I went to the bank today and found that my account was empty. Then I went to the riverbank and cried. So the word bank shows up twice but they have, again, very different meanings. And the question is, how do you distinguish which one, right? How do you know which one is the financial institution where you store your money, or depending on how you see it, they steal your money, and the other one, the riverbank, which is usually quite a nice place to have a picnic. So we do this by simply looking at the context of the word, as well as how it fits into the sentence. So if I see the word my account, then the word bank, I would immediately think it's the financial institution where I store my money. And some of these other words, like I went to, or today, or I found, those are also words which contribute to me making a decision about what that word bank is in the context. Is it the financial institution, or is it sort of the place where I like to have my picnics and spend some time with some friends? And so we're basically using some of the words in the sentence to we're paying attention to different words in the sentence with different emphasis in order to make that context awareness. So inside, if we look at the hood, underneath the hood, this is what's going on with the multi-headed attention. You'll see that there are basically like 3 linear layers, some matrix multiplication, scaling, softmax, and basically some processing. If we look at our linear layers, you're going to say, well, what the heck do we put in there? Well, we put in our embedding vectors. So we'll need to transform that first because of the size. We want the stuff to go through properly. And when we feed it in, it's basically going to the neural net is going to transform that information into new embeddings, so as EP prime, let's say. So here, if you look at what the neurons do, these are, again, weights. And these are, again, at the beginning, they're just random numbers, but over time with training and with backprop, you actually get better. Those numbers will scale down and stabilize. So the linear layer is basically to convert out to change the size, but it also implants some information. The three, you're going to say, well, why do you need three linear layers? You basically need three for the query, the key, and the value. What the heck are the keys? And what the heck are the queries? And what's value? So this is basically motivated by retrieval systems. If you think about YouTube videos, this is how it works, right? So you basically type a query in, right? You ask them, look for this. And what it does is that YouTube is actually going to look into its database. And it's going to return a set of keys. These are sort of hooked up to the titles, right? And they say that if, and the values are basically the content of that video. So now the million-dollar question is, well, how do you match these keys with the query? Like, how do you know which one, right? Which is the most similar? So again, if you're doing a search on YouTube videos on 17th century mathematics, you'll see that most of the titles which are getting returned have the word 17th century and some mathematics in there. So what does that mean? Well, we can use similarity as a proxy for attention. And so this is where the trick comes in. Recall that from your high school days that if you look at how two vectors, the similarity between two vectors could be measured as a function of its the angle and the cosine between them. So if two vectors are exactly the same, you'll have the angle at 0, and the cos of 0 is 1. That's maximum similarity. On the other end of the scale, at 180 degrees, you get -1. So you get this beautiful scale of telling you how similar things are. I just broke the cardinal rule. Usually we tell our students it's radians. I had to use degrees here. All right, so my apologies if you forgot what degrees look like and got used to working with radians. So so now we have this idea of similarity, which is sort of a proxy for attention. We can compute similarity between vectors, matrices, right? But the only difference now is that you have to transpose that matrix in the backend in order to ensure that your computations work out. And given that we're talking about queries and keys, those are matrices. So that's me writing the same formula, but with Q's and K's now. All right, so we feed, essentially we feed the input statement into the query and the keys. And what happens inside is that every single time we pass it through the linear layer, it's basically just going to do some type of matrix multiplication, right? And what is generated, what comes out of each layer are the query, the keys, and the value. Right, so you push that through, you get some matrices. And if we just zoom in just for the query and the key part for 2 seconds, if you push it through the matrix multiplication, what ends up happening is that if you multiply the query and the key together, you get this attention filter. So before we were looking at how those queries and the keys get mapped, now we're going to get the attention filter. So if we look at what happens with our example sentence, you'll see that when you multiply those quantities together, you'll see that the matrix is full of numbers, but at the same time, it pays it's essentially an attention matrix. And the words that each word is paying attention to is itself. It's basically giving you a score of how much attention you should be focusing on each word. Now, if we look at the word war and war, it's got the highest attention score. Why? Because it's got it's the most similar to itself. The next most similar word on this list will be probably want. Not sure why. Probably because of the W and the A. Then what we want to do is, then what the authors did was after they had this attention scores worked out, they divided by the square root of the dimension. And this is basically to stabilize the gradients, right? The values that you put through on the gradients. Here we go. So that's me computing those. Right. Okay, so then we want to put it through a softmax. And that essentially is going to change our attention filters and basically give you a value between 0 and 1 on what to pay attention to. So anything that is really not interesting, you just basically eliminate down and get squeezed down to 0. So basically that goes through the system. We then have a value and a attention filter that gets multiplied together. You're going to say, well, why the heck did we do all of that? Why is there 3 heads? The point is that each of these heads is going to learn something different about the words in general, or the word embeddings and the context of the sentence in order to generate a richer representation. If you stack this, you can get better prediction. matrix multiplication here. Then we're going to concatenate the vectors. Why? Because when you push these matrices through and multiply them, you're going to get these huge vectors. And so instead of sending a huge vector through, we're going to push it through another linear layer. That reduces the size again, and we're back out to the attention and the multi-headed attention unit. Now we're going to talk about the residual nets, which sort of hook up these things before we kind of move through the other elements. When we feed information into our network, we want to make sure that information that gets processed through the blue layer doesn't get lost when we get it through to the red layer. And so the question here is, how do we preserve that information? So it could be like positional information at the beginning, and we really don't want to lose that because some of these neurons are going to, each time you pass it through, it'll be different weights, different concentrations. And so we need to basically have a parallel highway. These are these residual connections, and then we'll pass it through. They'll add those together, and then we'll feed that through to the add norm layer. The add and the norm basically are taking the matrix for your embedded positions with the matrix that's generated from the multi-headed attention. You're going to add them together, and then what ends up happening is you're going to end up, you'll need to normalize the results. So how do we normalize that? We're going to simply just look at the average and the mean against each of the axes for the features. We're going to then take each element, we're going in the matrix, we're going to subtract the mean and divide by the square root of the standard deviation plus some small error, small constant, so that we don't go to 0 and have problems. So now we feed that forward. This is basically some linear ReLUs and another linear filter. Sorry, not filter, linear layer to basically process the data even further. So on the encoder side, you'll see that when you kind of do the reveal, there is this same architecture on the decoder side. The only difference here is that we take the imports, there's only one piece of information that the encoder takes in, that's the source text, and it produces this matrix. The decoder, on the other hand, takes in two things. It's going to take in the matrix, which was generated by the encoder, and it's also going to take in the output text that was produced before. So we have the source text, then generates a matrix. We're going to make two copies. Those are the queries and the keys. And then we're going to start it with the some type of start token, right? So this is how the decoder works. So with some start token, it goes in. Then it's going to get some positional information as well. Then we're going to head to the masked multi-headed attention, which we'll come back to later. We'll do some add norm. And this is where after you pass it through the masked multi-head attention unit, you can get another value key of that value matrix. That value matrix is then going to join up with the queries and the keys. They're going to then be outputted up to the feed forward, right? And then we'll do another add norm. We're going to go through a linear layer, then we're going to do a soft mapping and so forth. This last linear layer is basically where the classification happens. So if you want to classify just cats and dogs, there's only 2 neurons in your linear layer. And if you want to classify birds, you're going to throw a third one in. You can think of text generation as sort of a sort of a classifier, right? So our last linear layer is going to be the same size as our vocabulary, so think millions of words. And what you really want is you want to assign probabilities here so that you want to classify which word you get to pick out of the entire list. At the add norm layer, we're going to have some matrix. It's going to then get processed. We're going to push this through the input layer, and ultimately that's going to give us some vectors. But we don't want vectors. So, because we want numbers, we want to be able to process this information so that there's going to be a number that's associated to which word and then which one do I want to pick. So we don't want vectors here. What's going to end up happening is we're going to break up the matrix. We're going to concatenate it, and then we're going to push it through. And then what ends up happening is that we're going to get these numbers. And that kind of gives us a rough estimate for which word is the one that we want. So like here, we want to pick the word war because it's got the largest value. Okay, so again, that's a bit of a problem, right? Like I really don't want to be working with those kinds of numbers. Why? Because some of them are going to be negative, some of them are going to be positive. So we softmax it, and that's going to give us some probabilities. So, okay, so back to this mass multi-head thing. So what happens here? Well, here we want to be able to generate a sentence which is autoregressive, right? So I don't want to actually produce these words in sequence. I want this model to learn how to get that done. So here's how it works, right? So here's one of these heads zoomed in. So I have a matrix. Let's say I ask the question, how are you? And the answer is, I am fine. What you don't want is you don't want the word am, because you're kind of doing this backwards. You don't want it to have access to the word fine. And similarly for the word I, you don't want these other access. So you have this masking that occurs in the multi-head, the mass multi-head. So what it does is that it's going to essentially add this filter in, and the filter is going to be upper triangular full of negative infinities, lower triangular zeros, right? So essentially, if you don't want access to, you want this stuff to kind of survive, the bottom triangle, but the stuff up in the northern part of the triangle to kind of disappear. So we're going to basically squeeze this through with a lot of negative infinities. When you add these two matrices together, this is the result. Now this is what you're basically producing, this look ahead filter. When you softmax these negative values, those are going to get zeroed out. And essentially, well, this thing tells you how much attention to pay each word to be paying attention to. So for the word am, you don't want to be paying attention to the word fine. So you're going to assign a score of 0. And the same thing could be said about the I, right? You don't want it to pay attention to the word am or fine, so you assign a score of 0. And so that's how the filters work. And again, the way you're going to, the model will generate these words is that every single time there's a pass through the decoder, it's going to use the previous output until it generates the end token. And that will be the end of the sentence. So this is a really iterative process, and then you just get that ultimate end item. So where are we going with this NLP stuff, right? I mean, this is pretty cool. This is exciting stuff. I think that so far it's pretty good on language translation. Well, depends on the language you're speaking, and then like autocorrect, speech correction. I use some of these things in the slides today because my spelling is terrible. So thank God for spell check and autocorrect. Where we're getting there is sort of this text generation, and then the parts that still need some work are these common sense or extreme summarization tasks. There's some really interesting papers that are here. Maybe when we get to the networking later this afternoon, we can kind of discuss those. So where are we at? So here's what happened at 10:49 a.m. this morning. I went to our favorite transformer and put in our John Wick sentence. So you want a war, you just want to give me a gun. Lawrence Fishburne or the Bowery King says, someone get this guy a gun. Well, I think our transformer disagrees. It says you want to see the world burn or get rid of this guy, right? And so that is our transformer talk.